everyone, and welcome to the video lecture on Laplace transform. We have talked about the Laplace transform and we have gone through the Laplace transform of the various algebraic functions in the previous video lecture. Today we shall discuss some of the properties of the Laplace transform. So before discussing the first property, let us see how to get the Laplace transform of any function by making use of definition. So here I have written find Laplace transform of f of t, where f of t is defined as t from 1 to when t varying from 1 to 2, then 3 when t varying from 2 to 3 and 0 otherwise, right? So such type of functions can be evaluated, Laplace transform of such type of functions can be evaluated by making use of definition. Okay, so how to get this? So let us apply definition as we know definition. So let us use the definition. So it is by definition what we know, that Laplace transform of f of t is integral from 0 to infinity of e raised to power minus st into f of t. This is what we have according to definition, right? Now if we wish to evaluate this integral, what is required? We should know what is f of t. Okay, so f of t is defined in this way. We will make use of this definition. But what we are seeing that Laplace, this definition, this f of t is nothing but a defined in parts, piecewise continuous, right? So let us write this, split this integral as per the definition. So see here the limit, total limit given over here, okay, for this integration is from 0 to infinity. The complete integral given over here is from 0 to infinity. Okay, now just find out the points given for t over here. So 1, the next is 2, the next one is 3, right? No other points. So therefore this complete integral is divided into these 4 parts. So how will you write this? So we will write this as first part 0 to 1 e raised to power minus st. What is f of t from 0 to 1? Do you find f of t from 0 to 1? No, so it will come in the otherwise case. So what is f of t? 0. Okay, then plus next integral from next interval is 1 to 2. So 1 to 2 e raised to power minus st. What is f of t from when t varies from 1 to 2? It is t. So we write t. Then plus integral from next interval is 2 to 3. So we write 2 to 3. Okay. Then e raised to power minus st as it is. Put f of t. From 2 to 3, what is f of t? 3. Okay. Then plus integral from 3 to infinity. E raised to power minus st into f of t. 3 to infinity means more than this, so that comes over here, otherwise case. So what we have? 0. So we can write this integral in this way by property of definite integral. Okay, so this is done. What we find? The first and the last integral vanishes, 0. Here also 0, so this complete integration is 0. So we will just simplify the second and third one. So here we have t into e raised to power minus st. So this you can simplify by making use of successive integration by parts. So in the successive integration by parts, the algebraic function is taken as u and the remaining function is taken as v. Okay. Now let us recall quickly what is successive integration by parts. I have told you many times this formula. Still I am revising it once again. What is successive integration by parts? Integration of u into v with respect to x, integration of product where one of the function is algebraic. Then we write this as u into v1 minus u dash into v2 plus u double dash into v3 minus so on, where this dash is nothing but differentiation that many times. We have 1 dash mean 1 time differentiation, 2 dash so 2 times differentiation, and suffix, here we find suffix 1 2 3 like this. So suffix is nothing but integration. Suffix 1 means 1 time integration, 2 means 2 time integration. Okay, so let us see how to apply this formula. So this is successive integration by parts. Okay, now so let us apply successive integration by parts in the first term, which is left over here. Okay, so what it is? So it is u is t, so you write t. v1 means integration of e power minus st. So it is e power minus st upon minus s. Apply the formula of integration, right? Okay, then what we have? Minus. So this is our first term, and this entire term is second term. Minus u dash means derivative of this previous first term. So derivative of this t is 1. Now v2 means how will you get v2? So you will integrate this v1 once again, so you will get v2. So let us integrate second term once again, or the previous term. So e raised to power minus st upon minus s, already minus s is there, so s is square. Then next plus, now u double dash, how will you get u double dash? If you differentiate this previous first term once again, so differentiate this one, you will get 0. So in this way, integration of the first term, this term is complete. So integration complete, so we will apply the limit. That is, limits are 1 to 2. Okay, the next one. In the next integration, what we have? 3 constant. Integration of e power minus st. So 3 constant. Integration of e power minus st, e power minus st by minus s. And we will apply the limit. What are the limits? 2 to 3. Okay, then just apply the limit. Put upper limit 2 for t in place of t. So we have minus 1 by s. Then it is 2 e raised to power minus st by applying upper limit. Then apply lower limit 1. So we have minus 1 into e raised to power minus s. Put ts2 and ts1. Right? Then next minus 1 by s square outside. Put upper limit. So e power minus 2s minus e power minus s. Okay. Then minus 3 by s is constant in the next term. Apply integration. So it is apply limit. So put upper limit, that is 3 e power minus 3s minus e power minus 2s. Okay, so in this way we have substituted the limit. If you wish, you can further simplify, look for the similar terms. So I don't think so that is there any similar terms. Yes, we have the similar terms. What are the similar terms? Okay, so there is only one term of 1 by s square. Let us write that. So I'll write it as e raised to power minus s plus e raised to power minus 2s upon s square. This we have written. Now then e raised to power minus 2s plus 3 by s. Here it is minus 2 by s. So what it will be? Plus 3 by s minus 2 by s. So it is only 1 times 1 by s of e raised to power minus 2s. Okay, now next. Minus minus plus e raised to power minus s. And here what is left? Minus 3 e raised to power minus 3s. So this is what is the required Laplace transform. So Laplace transform of f of t is equal to this according to the definition, right? Okay. So now let us move to the next important concept, that is properties of Laplace transform. Now these properties are useful when we have a number of operations to be performed. That is, say for example we want to add two function of t, we want to have the scalar multiplication or a simple multiplication or division by t or integration and derivative. So these properties you will find useful. So let us see these properties one by one. So Laplace transform of properties of Laplace transform. So let us have the first property. The first property is called the linearity property, right? The first property is called the linearity property. So the first property, linearity property. So the first question that you should ask is that when to apply this property, right? So we can apply this property when we have a number of terms in addition of function of t, right? When a number of function of t are in addition, or there is a scalar multiplication. Scalar multiplication means the function of t is getting multiplied with a constant, then that is called scalar multiplication. So when we have a number of terms in a addition or in scalar multiplication, then we use this linearity property. This is very important property. So what this property says? So it says that if Laplace of f of t is equal to say f of s and Laplace of another function say g of t is g of s, then Laplace transform of alpha into f of t plus beta into g of t is equal to alpha times f of s plus beta times g of s, which can be also written as or alpha times Laplace of f of t plus beta times Laplace transform of g of t. It means what? When we apply Laplace transform on a function of t where we have certain constants, so that constant will go out of the operation. So Laplace transform operates only on function of t, right? This is what the property says. Now this property can be extended when we have a number of terms. Say, so in general, let us first prove this property. So proof. So we will go according to definition. Remember, most of the properties are proved by making use of definition of Laplace transform. So far what we have discussed is only the definition, and we have derived the Laplace transform of some of the algebraic functions. So here we make use of only the definition, right? So by definition of Laplace transform, what will be Laplace transform of? Consider this left hand side. So it is alpha f of t plus beta g of t is equal to what it will be according to definition. Integral 0 to infinity is fixed in a definition. E raised to power minus st is also fixed. Now we want Laplace of this term, so we will write this entire term in place of f of t, right? So here f of t is nothing but this complete term. So it is alpha f of t plus beta g of t. Okay. Now what we can do? Here we have a number of terms in addition inside the integral, so we can apply the property of integral. So what we can do? We can simplify this as equal to, this is nothing but integral 0 to infinity e raised to power minus st into alpha f of t dt plus integral 0 to infinity of e raised to power minus st into beta g of t. Okay. Now alpha being a constant, why alpha is constant? Because integration is done with respect to t. So any term which is not containing t will be a constant. So alpha is constant. Take it outside. Integral 0 to infinity e raised to power minus st into f of t dt plus here also beta is constant, so it will be going outside the integral, e raised to power minus st. Here we have g of t dt. Okay, now look at this according to definition. What this is? This is nothing but what? Laplace of f of t, right? And in the same line, this is nothing but Laplace of g of t. Right? But according to the notation, Laplace of g of f of t is nothing but f of s. S for notation. And this is g of s. So therefore what we are getting? Laplace of alpha f of t plus beta g of t is equal to alpha times Laplace f of s plus beta times g of s. Okay, so this is Laplace f of t, Laplace of g of t, right? Or this is equal to alpha times Laplace of f of t in another notation plus beta times Laplace of g of t. Right? So you should remember this format, that Laplace of alpha times f of t plus beta times g of t is equal to, take out alpha outside, Laplace of alpha of t plus next beta outside, Laplace of g of t. So we can apply this property for to the number of terms when they are in addition or in scalar multiplication, right? So remember, when this property is to be used when we have addition or a scalar multiplication. Okay, so let us solve the problem based on this property, that is linearity property. Okay, so the very simple example which I am considering here is find the Laplace transform of. Remember, to solve the example we should require the Laplace one should remember the Laplace transform of those algebraic the common algebraic functions as well as the elementary functions, right? So find Laplace transform of t to the power half plus 2 times e raised to power minus 3t plus cos of 4t. Okay, so what we are having over here? Well, let us write it minus 6 times. Okay, right? So what we are having here? Laplace of number of terms are in addition and subtraction, right? And scalar multiplication. This function of t is multiplied with 2. Here also function of t is multiplied with 6. So scalar multiplication and addition and subtraction. So obviously we will have to apply linearity property. So let us apply linearity property. So therefore, right. So we have considered the term Laplace transform of t to the power half plus 2 times e raised to power minus 3t minus 6 times cos of 4t. Take the Laplace of first function. So it is no constant. So t to the power half. Then in the next term 2 is a scalar. Take it outside. Just take the Laplace of e raised to power minus 3t. Then in the next term minus 6 is a scalar. Write it outside. Then take the Laplace transform of cos of 4t. Okay. Now, what is Laplace transform of t to the power half? So here we will apply the formula Laplace transform of t to the power n. What is Laplace transform of t to the power n? So it is gamma of n plus 1 upon s to the power n plus 1. Okay. because here n is what? N is a in fraction. If it is a positive integer, then we will apply the formula n factorial upon s to the power n plus 1. Otherwise, we apply this formula. Okay. So, just find out the value of n. What is n here? N is half. Okay. So, n is half. So, put n as half. So, we have gamma of n plus 1. Half plus 1. So, that is gamma of 3 by 2 upon s to the power 3 by 2. Okay. Plus 2. Then, what is Laplace of e power minus 3t? Yes, Laplace of e power minus 3t. So, here we will apply the formula Laplace of e power minus 8t or 80 simply. What is Laplace of e power 80? 1 upon s minus a. Right, just identify a. What is a here? A is minus 3. So, what it will be according to that formula? 1 upon s minus of minus 3, that is plus 3. Isn't it? Minus 6. Now, Laplace of cos 4t. So, we have the formula Laplace of cos alpha t. What is Laplace of cos alpha t? Laplace of cos alpha t is alpha upon s upon s square plus alpha square. Okay. So, just identify alpha over here. What is alpha? 4. So, what it will be? S upon s square plus 4 square, that is 16. So, in this way, just by making use of the Laplace transform of elementary functions, one can get the Laplace transform by making use of the linearity property. So, what we have used here? Here we have used by linearity property. You can write this down in this way. Okay. If you wish, you can simplify it further. Otherwise, this much is sufficient. Okay. Okay. Let us move to the next one. Next example. So, the next example is find Laplace transform of sin square 3t. So, observe this expression carefully. In our algebraic functions, we have Laplace transform of sin alpha t and cos alpha t only. We don't have the term formula for sin square, right? So, what we will do? We will make use of the trigonometric formulae to reduce this given expression into the form sin alpha t or cos alpha t. Let us see how it can be done. So, solution. So, we know that sin square theta. What is sin square theta? Sin square theta is 1 minus cos 2 theta upon 2. Okay. Now, identify theta. Theta is here t. So, this implies sin square 3t is equal to 1 minus cos 2 into 3t, that is cos 6t upon 2. Right. So, we want Laplace transform of this. So, taking Laplace transform on both the side. So, Laplace transform of sin square of 3t is equal to Laplace transform of 1 minus cos 6t upon 2. Here I am observing that there is a scalar, one scalar. What is that? 1 by 2. Take it outside completely. Then Laplace of what we have? 1 minus cos 6t is left. So, here what I have applied? I have applied property, linearity property for scalar multiplication. Alpha into, I am considering this function as a completely f of t. So, by linearity property, again, here I am finding two different terms in addition or subtraction. So, again apply linearity property. So, we have 1 by 2 times Laplace of 1 minus Laplace of cos 6t. Just apply the formula. So, it is 1 by 2 times Laplace of 1 is 1 by s. In Laplace of cos 6t, just now we have seen it is what? S upon s square plus alpha square. What is alpha? 6. 6 square is 36. So this is nothing but a required Laplace transform. So in this way, by making use of the property 1 and the Laplace transform of the elementary function, one can get easily the Laplace transform of desired function. Thank you for watching the video.